So, good morning, everybody. Thanks a lot, Hans-Peter, for the nice introduction, and of course, especially for the invitation to give this series of lectures here at the data center. So, yeah, the topic of the lecture is new approaches to Feynman integrals, and what exactly we're going to talk about. We'll see a bit during the course of the lecture. So maybe let me first share my screen. Here we go. So, can you see the screen?
Yes, we can see the screen.
Great. Okay, so the title of the lecture is New Approaches to Feynman integrals. And while during this first hour, well, first 45 minutes, we will define what all of these concepts are, especially what Feynman integrals are, and also a bit why we need new approaches to calculate them. And then, yeah, let's maybe first get started and define the background of the lecture, and then we see at the end of the lecture of what the actual content of the lecture will be. So maybe let's start from the beginning. Hans-Peter already mentioned that what I'm mostly interested in is something called scattering amplitudes. So what are they? Well, so imagine you're working for the LHC and you want to make predictions for a collider like the LHC. So the LHC is a proton collider, so you have two protons coming in, one on each side. And, well, you make them collide. Now you know that protons are made out of quarks and gluons. They are non-perturbative objects. So in the end, what you have to do is you want to describe it as a collision of quarks and gluons. So you take, for example, a quark out of one proton, you take a quark out of another proton, you make them collide. And, well, the non-perturbative structure of the proton you cannot calculate because it's non-perturbative. And whenever you hear non-perturbative, it usually means that there's no easy way to calculate, at least put it like that. There are approaches from lattice, but let's not go there. So non-perturbative objects you can't calculate. What you can calculate is something in perturbation theory. And so what you can calculate is the collision of your two quarks. For example, if you took out of the proton and you make those collide, and they produce a certain final state, X. So that is something that you can calculate. And, well, the way you calculate it is, well, it's quantum mechanics. So what you calculate in the end is probabilities always. And there's a theorem that tells you that in group approximation, the cross-section, the probability that you want to calculate contains three pieces or two pieces, which are these Fs, which describe this non-perturbative structure of the proton. Those you can't calculate from first principle. You have to essentially extract it from data. And you multiply this by the cross-section for the collision of the quarks, which are the constituents of the proton, to produce your final state. So in the end, what I'm interested in is just this piece here, just this cross-section for the partons, meaning the quarks and the gluons, to collide and to produce something. And cross-sections, as you probably remember from the quantum field theory lectures, are always given as take the amplitudes, the sum of all Feynman diagrams, you square them. So that's just quantum mechanics. You have to take the wave function and you square it. You take the amplitude and you square it. And then you have to integrate over what's called phase space, which essentially means you have the sum of all possible final state that you could reach. So this is just the general way you make predictions for colliders. So essentially you compute cross-sections. So that is what I want to do. I want to compute cross-sections for the collision of quarks and gluons, which is what we need for the LHC. And to get those, I need to do this phase space integral of the square of an amplitude. And this amplitude is a scattering amplitude. It's probability amplitude that describes the scattering of particles. So that's what we want to do, calculating scattering amplitudes with external quarks and gluons. Now, we don't know how to do that exactly. The best we can do is perturbation theory. As I said already, whenever something is non-perturbative, there's no way you can calculate. So what can you do? You essentially approximate the amplitude by a series. And the series is organized in terms of Feynman diagrams. I guess many of you know what they are, or at least have heard about them in some quantum field theory class. So the leading order of your amplitude would be the tree-level diagram, which would be something like this. So that would be, for example, two quarks coming in and they interact by exchanging a gluon. That is something that is easy in the sense that we know how to do it. So I'm not going to talk about that. That's something that, in principle, we all know how to do. Easy in the sense that one knows how to do it. It may not be easy when you have to actually do it, but at least there's a known solution for this problem. And the next order, well, it's quantum mechanics. So you always have to sum of all possible intermediate states at link initial and final states. So for example, your two quarks may decide to exchange a gluon before they collide. So what you actually get is naturally, at the next orientation, you have that have a single closed loop. So those are loop diagrams. And these diagrams that have a single loop, one loop diagrams, they are hard to compute. They are not easy anymore. But they're also not extremely difficult in the sense that it's well understood how to do that. At least, say, for all practical purposes, it's something we know how to do. It may be technically very challenging, but it's something we have under control. That's all what we're going to talk about. What I will talk about is contributions where you have two or more loops. So for example, your gluons may exchange yet another gluon. Now you have two loops in your graph. There's one here, and there's one down here. So you have loops in your graph, your Feynman diagram. And that is something that is very hard to calculate, and we'll define hard in a second. And then, well, it goes on like this. Now the next order perturbation, you would have three loops. So now you would have, exchange three gluons, but at some point you may also, your gluons may split again into a quark and a quark pair. And this is something you can call very hard. We'll give a few slides. So those are the things I want to compute. Now, why is it hard? Well, it's a very complicated. So whenever you have a Feynman diagram with a loop, I guess many of you know that means you have to do integrals. And the reason is simply because, again, it's quantum mechanics, so you have to sum of all possible quantum numbers of all possible states that you can observe. So for example, if you take this diagram shown here, then, well, if the quark and the anti-quark exchange a gluon, you have to sum of all possible momenta that this gluon can have. And so, well, the momentum is a continuous variable, so you have to integrate over this momentum. And indeed, you can easily check that, well, momentum is conserved at every vertex in your Feynman graph, and whenever you have a loop, it means that there's one momentum that is not fixed by momentum conservation, because that is the one that is flowing around here. That is the one that you need to integrate over. Well, you have to sum of all possible values for this loop, so you have to integrate over. And I guess you all know how you translate Feynman diagrams into integrals or into analytic expressions. Essentially, every edge in the graph, well, an edge corresponds to a particle moving in space-time, roughly speaking, so it's a momentum. And you have to replace that by something called a propagator, which is essentially 1 over p squared minus the mass of the particle. And so whenever you have a graph, you just take all the edges in the graph and you multiply all of these propagators together. And then in the end, you have to integrate over the momenta flowing in these loops. So that's the basic rule. Now, if you have realistic theories, you would also have numerator factors. Let's not discuss those. You may know the example, the Feynman rules for QED, where you have these gamma mu factors in the vertex that couples the photon to the electron. Let's not discuss those. Let's just assume it's a scalar theory and all of our properties are. just p squared. So that is what we want to do. And so how hard is it? I mean, these are just integrals in the end. Well, one loop integral is said for all practical purposes, we essentially know what to do. And indeed, the one loop integrals have been classified, at least those that you encounter in four space-time dimensions. It goes back to the, well, to the 70s or late 70s by Toph and Weltman. Essentially, the only one loop integrals that you need in four space-time dimensions are the 2-point function, the 3-point function, the 4-point function. You can compute those once and for all, and you're done. It's a bit simplistic, but that's pretty much it. You go to two loops. Well, the 3-point function, which is shown here, and I'll show you now representatives, just to give you an idea of how quickly the complexity goes. This 3-point function was computed in the 80s. Then it took another 10 to 15 years, so 99, before people managed to compute the 4-point function. So it took almost 15 years to go from the 3-point function. But this was even the 4-point function where all external x, here, all 4 external x, or every particle in this graph is massless, not just external ones. Every single particle in this graph is massless. Just adding outside a particle that has a mass took another couple of years. So just adding one massive particle somewhere in the process took 2 years. Adding second massive particle took another 15 years. That is just to give you an idea of how complex these calculations are. And to add another external particle, so this would be like 1, 2, 3, 4, 5 external particles, all massless, took yet another 5 years. This was only done 2 years ago. And even something as simple as a 2-loop 2-point function where you have massive propagators, so here now all my internal lines are massive, that was just done some 5 years ago. So this shows you how complicated these calculations get. I mean, it takes, every time you want to compute a new integral, compute a new process, it essentially takes a decade. And to show you that, well, again, if you look at now, people are now thinking about 3-loop integrals, and there we're really talking again about things that are just a couple of years old. So this is just to give you a feeling for what the complexity is. So the complexity of these calculations is really such that, first of all, not many things are known. Well, many things are known, but you see 3 loops. I mean, not talking here about calculations at 20 loops, 2 loops, 3 loops. So these calculations get complicated extremely quickly. And part of the lectures is going to be about what is this complication and what have we learned in the last couple of years about the mathematics that goes into these computations and that can be used to kind of circumvent or solve some of the problems that you get if you try to do these calculations. Because I guess for this growth in complexity, you can feel that if you just take, well, what you've learned in quantum field theory 101, so you go to the appendix of Peskin and Schroeder, it tells you how to do loop computations. That may be a way to do it for 1-loop integrals, which is what you started Peskin and Schroeder, but if you try to do 2-loop computations already, you're most likely going to fail. So the mathematics that goes in there is actually pretty challenging, and that is part of what the lecture is going to be about. And that's also, now in this first part, we will see what is the kind of mathematics that we encounter, and then we will dive into this mathematics a bit more in other lectures. So what is the kind of challenges that you get with the kind of mathematics? So why is it so hard? Well, one problem is that there's a combinatorial problem. And that one is easy to understand. I mean, for your amplitude, you have to sum up all possible Feynman diagrams that contribute to a process. And so just to get a feeling for how complex the calculation is, just count the number of Feynman diagrams. For example, let's count the number of Feynman diagrams that contribute to Higgs production. So this would be two gluons that collide and produce a Higgs boson. And let's count the number of Feynman diagrams that you need to calculate. In the first order in perturbation theory, there's one diagram. Two gluons collide, produce Higgs boson. That's all that is. For the expert, I'm talking here about the limit where the top quark is infinitely heavy and is integrated out. So just to, that's for the common for the experts. If you wonder why I just say there's one diagram. If you go to the next order in perturbation theory, which is often called NLO, next leading order, well, you have 100 diagrams to calculate, the order of 100 diagrams. That may sound a lot, but if you now check what happens if you go even to higher orders, NLO, that would be next to next leading order, you have even 10 times more. And if you go to alpha, well, to the third order in the strong coupling, the third order perturbation theory, you have of the order of 100,000 diagrams. So you see that the number of diagrams that you need to evaluate is just, it goes extremely quickly. It just explodes. And so that is one of the reasons if you just try to do it, the textbook approach, and you sit down and you write down every single loop diagram and you try to evaluate it, you're not going to succeed. Because yes, you can do that maybe still for 100 diagrams, but for 100,000 diagrams, no way. So you need another way of capturing the complexity in there. Just writing down every single diagram and evaluating every single diagram is not going to work. Okay. If you have any questions at any moment, please stop me. You can also raise hands, but then I may not see it because I don't see the chat right now. So either one of the organizers needs to keep an eye on the raised hands, or you just speak up. That's not a problem. So that is one problem. There's a combinatorial problem. But then even if you get that under control, there's a problem that the integrals are very tough. They are not integrals that you do easily. And one reason is, well, these integrals, as you probably know, are often divergent and they need to be regulated. We'll come to that briefly. But one thing that you can get from that is that since they diverge and need to be regulated, numerical integration can be very tough. It's not an integral that you just put on a computer and you let the computer evaluate it. You let it run for a long time, because that's most likely not going to work because the integrals diverge and you have to massage them in special ways. And there are ways to do numerical integration of Feynman integrals, but that can be very tough because these integrals often diverge. Okay. So this was what I wanted to say as introduction. So those are the things we want to compute. So now we will look at what Feynman integrals are more precisely. I will now define these quantities mathematically. Before I do that, are there any questions? Okay, don't see any. I mean, if you again, if you raise hands, I don't see it. Good. So then let's try to get a feeling for what Feynman integrals are. I mean, let's be more concrete. Let's define things. So for simplicity and a bit for the expert, I will only talk about scalar integrals. What that means is that these integrals are, well, those are the integrals that I will define now. For the experts, or you may know it from the field theory class, there's something called tensor reduction, which in principle allows you to reduce every other integral to such a scalar integral. So what is such a scalar Feynman integral? Well, we said I need to, first of all, I have propagators, which are in the denominator, and I need to multiply them together, and I give you a Feynman graph. I multiply together the propagators. Every propagator has to form 1 over p squared minus m squared. The momenta flowing through an edge are always linear combinations of what I call here k, which are the loop momenta, and p's, which are the external momenta. So from now on, I will always use the notation that k is a loop momentum, p is an external momentum. So that's one of the external particles. And of course, we also said in a realistic theory there are numerators, and so here there should also be some numerator factor, which I call n, which is always a polynomial. It's a homogeneous polynomial, even homogeneous because the integral has a well-defined energy dimension. I mean, p and k carry an energy dimension, so the numerator has a well-defined energy dimension. And so it's a scalar integral, which means that the numerator should only depend on the scalar products between loop momenta or loop momenta and external momenta. That's all it is. So that's the most common thing I can write down. And then we said, well, I also need to integrate over every loop momentum. And that is my Feynman integral. So that's the most general thing I can write down. And let me point out something here, which I will introduce here, which may sound a bit ad hoc. I introduce exponents to my propagators, which are integers. So actually what I'm going to do is I'm going to consider more general quantities than what I would naively expect from Feynman from quantum field theory. I allow propagators which have arbitrary numerators. Sorry, exponents. Why do I do that? Well, we'll see that a bit later.
So
for now,
you allow for negative integers also.
Sorry?
You allow for negative integers also.
Yes, that's a good comment. That will be important later. You see, it's not a problem. It's not even a restriction because if one of these news is negative, it appears in the numerator. It would be part of n.
Yeah, okay.
And that is part of why I want to do it, because later on I can just forget about n and include enough denominators with negative exponents.
Okay, thanks.
Yeah, thanks. That was a very good comment. These exponents can be negative. We'll see that later, also why they're introduced. For now, consider it as part of the definition of the object that I want to study. So that's the object I want to study. So what do I know about it? Just on general grounds. Well, we said they are scalars, so they are Lorentz invariant. That means that the result of the integral will only depend on the dot products between external momenta. So the integral depended on dot products between external and loop momenta. The result of the integral, I, will depend on dot products between external momenta, because it's a scalar. That's a trivial statement at this point. The other thing, which we already said, is that these integrals may diverge. You need to regularize them. And the way I'm going to do it is, well, many of you may have heard about this or at least seen it in some lecture. If not, it's not so important. I'm just going to tell you that there's something called dimensional regularization. And the idea is that you treat these integrals as not living in 4 dimensions, but in some arbitrary dimension. And I introduce a little epsilon, which parameterizes how far away I am from 4 dimensions. And the claim is, and you can actually prove this, that if you do that, if you look at these integrals as functions of the dimension, then the integral actually converges. And it's only when the dimension takes specific positive integer values that the integral diverges. More precisely, so this is not more mathematical, you can actually show that int is a meromorphic function of the dimension with poles at specific locations. Actually, I should say here, poles. Okay. And well, if you're not familiar with this, maybe we can go to the details during the discussion session this afternoon. I don't want to define dimensionalization in full glory because I guess many people have at least heard about it in quantum field theory lectures. What you should remember from it is that the divergences are regulated by introducing this little epsilon here, which characterizes the deviation from 4 dimensions. And in the end, what I do is, well, I now consider my integral as a function of epsilon. And I look at it as a series expansion in this epsilon, where if the integral diverges, then the series starts with a negative negative power of epsilon. So it starts like 1 over epsilon as epsilon goes to 0, and if epsilon goes to 0, the dimension approaches 4. The thing you should remember is that I will always think about integrals in this way. They are always these series, they are Laurent series in this parameter epsilon. And the only thing that you care about are the coefficients in the series, these IKs, for relative small values of k, because I don't care about the first 100 terms in the expansion. I only need it up to the term which is epsilon to the 0, because then I'm in 4 dimensions. Okay, so that's what I care about, not what I want to compute. Okay, so another thing which is pretty obvious is what we already said it is every integral has a well-defined energy dimension. And you can easily check that the energy dimension of an integral is, well, L times, so the number of loops times the space-time dimension. It's just the integration measure, ddk1, ddk2. So for every loop, I have d units of energy. Every propagator is 1 over p squared raised to some power nu. So that gives me something in the denominator. And then there's, of course, also this numerator factor that I included. So, and it said n is a homogeneous polynomial. So n has also a well-defined energy dimension. And so I has a well-defined energy dimension. This is important, trivial, but important consequence, which is the following. So my integral will depend on the dot products between external momenta, which I can call scales, energy scales. Let's say there are S1 to Sk scales. This would S1 would be P1 to P2, S2 would be P1 to P3, and so on. So our integral will be a function of these S1 to Sk. But you can easily convince yourself that since my integral must have a well-defined energy dimension, it actually is only a function of k minus 1 variables, which are the ratios of these energy scales. Well, I can pull out one scale raised to some power, which is precisely the energy dimension. So there's always one variable less in the problem that I have energy scales. It's a rather trivial observation, which will, however, have important consequences. Okay, so if I have something that depends on 2 scales, S1 and S2, it would be S1 to some power times a function of S1 divided by S2. That's the idea. Now, the first important consequence of this is the following. What if k is equal to 0? What if there's no energy scale whatsoever? Well, 2 statements, the fact that I can always have a well-defined energy dimension and the fact that there's no scale in my integral can only work if essentially my I tilde here is 0, if k is equal to 0. That is a very important thing, which only holds in this regularization scheme dependent statement, which says that if an integral does not depend on energy scales, then the integral is 0. It's a weird thing, but you can actually prove it mathematically. If the integral does not depend on any energy scale, it vanishes. And I insist on this first thing, which says in-dimensional regularization. In other schemes, this would not be true. Good. Another thing which you may know is something called Feynman parameters. This is often introduced in your quantum field theory lectures by essentially combining propagators. So let's maybe In quantum field theory, you often see things like this, that 1 over AB, you can write this integral from 0 to 1. I think it's dx over xa plus 1 minus xb squared, and then there's some numerical factor here. Okay, and you can use this to combine propagators. If A and B would be propagators, you can replace propagators by applying this recursively by these integrals over x, which are called Feynman parameters. The x. So if you do it recursively, you would have an x1 and x2 and so on, which are called Feynman parameters. Now, I'm just giving you here a way of writing this, which is a bit more mathematical. For those of you who like the more formal thing, you can actually show that, yeah, let's do not go there. So there's a way of writing this in terms of what's called graph polynomials. But there's this Feynman parameter representation. In the end, you write your integral as an integral of a rational function of the Feynman parameters. Let's just jump over this. There's a way to represent this. You can look at it in more detail. It's a bit more mathematical, but it's what you know from quantum field theory, big formulas. Good. So that's pretty much all you can say on general grounds about these integrals. Are there any questions about what we've said so far? Okay. So then, well, I've told you now a lot of abstract things about what we expect for these integrals. So, but let's look at a concrete example. Okay. Just to get a feeling for what we expect. So what objects do we expect to get? So let's take an example. Let's take this 3-point function. Okay, it's 3 external momenta, P1, P2, P3. Momentum is conserved, and I use the convention that all the momenta are ingoing. So momentum conservation tells me that these momenta sum up to 0. And I also assume that all the particles are, the internal ones are all massless. And you can easily write down the Feynman integral that corresponds to this graph as shown here, right? That's the 3 propagators. And then I integrate over the momentum flowing here in this loop. So that's pretty standard. Now, what do you get? That's the question. Now, in general, these integrals will diverge, and I cannot do it in 4 dimensions. Here, do it in 4 dimensions. This integral is convergent. So this I can live with putting here d equals 4, just as a side point. But in general, I could not. So let's see what we get. Well, we said, first of all, that these integrals are Lorentz invariant. So they can only depend on the dot products. So the dot products here would be, well, P1 squared, P2 squared. P3, I don't need to consider because P3 is minus P1 minus P2. And then there's, of course, also P1 dot P2, which is the same as, well, you can use this. So I can either work with P1 square, P2 square, and P1 to P2, or with P1, P2, and P3. Okay, so those are the only Lorentz invariants that I have. And so I choose to work with P1, P2, P3. And we also said that by dimension analysis, the function can only depend on ratios of my scales. So it will only depend on well, I had 3 scales, P1 square, P2 square, P3 square. It can only depend on 2 ratios, which are called U and B. So that's as far as we got before, right? We said that there's some, well, there would be some, say, P3 squared to some power times a function of U and B. Okay, so that's what this integral should be. Now, what function of U and B? At this point, I have no idea. Just said, okay, it's a function of two variables, which I call u. Could it be anything? Right? Could be anything. Could be as simple as you like, even, right? Maybe it's a polynomial. Maybe it's just, I don't know, u times v. But one thing that you learn just from quantum field theory is that it cannot be simple. It cannot be simple, and the reason is unitarity. Why? Well, you may remember from quantum field theory that there's, well, unitarity in the shape of the optical theorem says that if you take an amplitude for a process, this here, then this function must have discontinuities, must be a multi-valued function. So there's discontinuity. And this continuity is precisely proportional to putting intermediate particles on shell, so putting the propagators on shell. So this means that whenever I have loops, it cannot be a simple function. It cannot just be u times v or u squared or something like that, because it must be a function that has discontinuity proportional to 2 pi I. And this is physics. This is quantum field theory. This comes from internal particles that can go on shell. Okay, so it just tells me, just by pure thought, just from quantum mechanics, I know that these integrals cannot be simple. Now, this is the answer. And we will dissect it a little bit to get a feeling for what it contains. So the first thing that you see is that, well, in the answer, there is not u and v that appears, but it is these quantities z and z bar. So here, z bars, the z's, which are related to u and v just by the simple change of variable. Okay, you can easily invert this relation and get z equals z bar. But then you see there's other stuff. So the first thing that you see is there's a logarithm showing up. Logarithm, I just defined it for you here. It's the integral of, say, from 1 to x of 1 over x. Log of 1 minus x is the integral from 0 to x of 1 over x minus 1. So that is one thing that shows up in here. So it's logarithms. And that sounds about right, because we said that these functions should be functions that have a discontinuity proportional to 2 pi I. And indeed, you know that the logarithm has its, well, whenever you cross the negative real axis, its value jumps by 2 pi I. So there's a discontinuity of 2 pi I. But then there's other stuff. There's this Li2 here. It's underlined in red. It's called the Duhr logarithm. Well, that is something a bit, maybe, well, unusual. At least, maybe, don't think that everyone has seen it before. It is a function which is defined also by an integral, also from 0 to x, so Li2 of x, from 0 to x. And then you see, it looks a bit like iterating the logarithm. So there's the logarithm, which was the integral of 1 over t, which is here. But you also have another logarithm in the integrand. Or I can also write it as, if I insert the integral representation, I can also write it as a double integral. Now you may be tempted and say, well, do the integral properly and don't call this Li2. You can try as long as you like. He will not be able to do this integral in any form in terms of elementary function. This function Li2, the Duhr logarithm, is a new fundamental function. Something, it's an integral you cannot do in terms of elementary functions. It's a new function. So there you see that even at one loop already, things get non-trivial. And now, yes, you can imagine, if you go to more loops, you have more integrals, so you could iterate this even more. So instead of just having, before we had in here Li2, then Li1, and Li1, I call it a log. This is a definition. But now I could go on. I could use the same construction, put Li2 in the integrand, integrate it once more, and so on. And so I can even go on and I can add, well, here you see the position of the pole was always at 0, but I could also shift the pole a bit. I need more variables at some point. This gives me then even more functions. They all generalize the logarithm. For example, here this function generalizes. Well, we'll study these functions in much more detail tomorrow or the day after tomorrow. But those are all kind of things that show up. And it doesn't even stop there. At some point beyond one loop, you get to things like, also it's called elliptic integrals, which are shown here. Here's one example of what's called an elliptic integral. And there are also things called elliptic polylogarithms. So there are these polylogarithms which we just defined here. And there's elliptic integrals, and then you can even mix them. You get something completely new. Elliptic polylogs, you get things called modular forms, and you get a whole zoo of things. So it's something that also mathematicians are often very interested in, because studying these integrals that you get from physics are really a laboratory to study all kinds of new functions and integrals that also mathematicians care about. In the other direction, that also means that there's a lot of mathematics that is known about these integrals. And that is partly what this lecture is going to be about. It's about what kind of mathematics do we know, and what does modern mathematics tell us about these integrals, and how can we use very cutting edge mathematics to calculate Feynman integrals? And this, as we will see, this goes far beyond what is in Peskin and Schroeder. So the mathematics that is in there is, I would say, both fascinating and also sometimes daunting. Okay, so I think this is a good place to take a short break before we go to the next topic. So we can take a short break, and we start at 11. But before we take the break, I mean, I guess this is also a good time to ask any questions in case you have any. Okay, I don't hear any questions, so I guess then let's take a little break, and then we restart at 11. So then, good. So in the first hour, we basically just gave an overview of what Feynman integrals are, what kind of objects we get when we evaluate them. And well, we briefly defined these things: logarithms, polylogarithms, that I mentioned here in this slide, other objects. We will encounter them and study them in a bit more detail later. So if it was too quick, don't worry. But the thing that you should remember is that Feynman integrals cannot give you easy functions, not simple functions. They must be functions that have discontinuities. That's a consequence of unitarity. And the prime example is the logarithm, and that normalization of polylogarithms. And again, we will study them in detail later on, so don't worry if you don't remember the definition right now. And then even more complicated things. And just as a general idea to give you, well, I think it's a neat result, and that's why I want to discuss it. There's this whole zoo of objects that people have found when they look at integrals. And so you can play the following little mind game. You can say, well, is there any kind of bound that are on the objects that I could get? And so if you evaluate a Feynman integral, what kind of numbers do you get? Or turning it around, if you take a random number, what is the probability that that is the result of a Feynman integral? That's the more provocative way of putting it. And to get a feeling for the answer, you need a notion that was introduced by Maxim Kontsevich and Donzaghi some 20-ish years ago, I would say. So Donzaghi is in Bonn, actually, a mathematician in Bonn. Maxim Kontsevich is a mathematician in Paris. And the notion that you need is this notion of a period. So what is a period? Well, I guess you know from physics what a period is, but there's also mathematicians have defined this idea of a number, which is a period. And it's, well, it's a complex number that is an integral. Integral of what? Well, an integral of a rational function. And a rational function, it should be a rational function. The coefficients in this rational function should be rational numbers. And well, to define an integral, you need two things. You need an integrand and an integration region. And the domain is given by, again, inequalities of rational functions. So it's essentially an object that is defined by rational functions. And you write down an integral of a rational function integrated over a domain, which is defined by rational functions. We'll see an example in a second. As a side comment, you can replace this definition rational by algebraic everywhere. If you don't know what algebraic is, we can also, in the discussion session this afternoon, discuss this point. It's roughly speaking things that involve square roots.
I have a question.
Yeah.
So if I have one of these integrals and let's say it gives me the answer 1, then I can multiply the integrand by any number, and then I'll get an integral which gives me any number.
Yeah.
But that's trivial, right?
That's trivial, yeah. But so that, I mean, the number that you well, maybe let's wait 2 slides and then I come back to your question.
Okay.
So maybe let's do that first then. Maybe let's first look at examples of periods. This then connects to Herbie's question. So what are periods? Well, one thing that I didn't write down here because it was in the previous slide is that every rational or algebraic number is a period. So 1 is a period. If you multiply 2 periods, you get another period. So as long as you multiply, for example, your 1, which was a period, by something which is of the same type, you get a period. If you multiply it by something which is not a period, it will not be a period. So it's important in this definition that it was an integral of a rational function, integrated over something that is rational. I don't know, Herbie, does this answer your question?
Not really. I mean, in the beginning you were saying that, is there, if I give you a number, can I always write down a Feynman integral that gives me that number? And if I can get one that gives me 1, then I can just get anything by multiplying.
Okay, then yeah, let's wait another slide and then
Okay.
the answer will be that the probability that if you take a number at random, the probability that it is a Feynman integral is 0.
Okay.
And you will see why. It's a little mind game, but I think it's a fun mind game. Actually, that's just to show the Feynman integrals are very special. If you just take a random number, the probability that this number is a Feynman comes from a Feynman integral is 0. But what numbers are these periods? Well, one example would be pi. Why? Because pi, it's the area of a disk, which I can write as the integral of 1 times dx dy, integrated over the interior of the disk, which is given by x squared plus y squared less than 1. So that is clearly it's the rational function 1, which sits in the integrand, multiplied over this domain, which is given by an inequality of rational functions. So pi is a period. Another example of a period is logarithm of 2, for example. Why? Because I can give it as integrating dx over y, which is clearly a rational function, over the range from 1 to 2. So that is given by, if you want the inequality, 1 less than x less than 2. So there's clearly an inequality of a rational function. So log 2 is a period. Note that this shows already that when these two here are irrational numbers, so periods are something which they are irrational numbers that are periods. You can also show that all these polylogarithms are periods. more generally, and that is now, well, you can show that every rational number is a period, but not every complex number is a period. There are complex numbers that are not periods. This Q bar here, if you don't know what it is, it would be the algebraic numbers. Those would be things like square root of 2. You can also show that if you multiply two periods, you get another period. So the set of all periods is a ring. And you can show that there's a countable number of periods. That is the reason why this inclusion here must be strict. So why is there only a countable number of periods? Well, because periods were defined by rational functions and rational numbers. But how many rational numbers are there? There's a countable number of them because they have ratios of integers. So there's a countable number of integrals of rational functions I can write down. So there's only a countable number of different periods. It's a bit hand-wavy, but give you a feeling. So there are definitely more complex, in general, there will be much more complex numbers than there are periods, because complex numbers from a continuum, there are uncountably many, while there's only a countable number of different periods I can write down. Or I can also phrase it then in terms of probability. If you take a random complex number, what is the probability that you pick the period? The probability is 0, because you have the measure of a countable set inside the complex numbers is 0. So if you take a complex number at random, it will never be a period. If you take as probability the standard, the back measure. Now, Feynman integrals turn out to be periods. This goes back to Stefan Weinzel and Christian Bogner. More precisely, remember that we said in the end, that work in dimensional organization, I have to look at these things as Laurent expansions. So they are expansion, this epsilon. But as a period are the coefficients of this expansion epsilon. Those are periods. The proof is both, I mean, when the idea of the proof is clear, it has to do with the fact that if you look at the integral, well, it's 1 over, if you write down the Feynman integral, it is actually an integral of a rational function, because the propagators are 1 over p squared minus m squared. Or you can also, if you want to be a bit more precise, look at the Feynman parameter space. Clearly, the Feynman parameter integral is an integral of a rational function. So it's clearly of that type. Where it becomes subtle is the fact that these integrals may diverge, you have to regulate them, and all of these things. That's why it's a bit more subtle. But the idea is just on the nose, quantum field theory gives you integrals of rational functions. So they will always be periods. And that's why I said, well, if you look at it from the perspective of probability, what is the probability that if you take a random number, is it a Feynman integral, or does it come from a Feynman integral? The probability is 0, because it must be a period, and we said probability that a random complex number is a period is 0. Now, then maybe now to come back to what Herbie, what you said, if I multiply an integral by some random complex number, I can get any number. But quantum field theory will only ever give me things that are rational functions. So that would not, in general, it will not be something they can get from quantum field theory. And that is where the key is. Quantum field theory, the Feynman rules are inherently rational objects. So I cannot just multiply by any number, because quantum field theory is built on rational functions. Does that answer your question, or? Good. So this was more of a little mind game to show you, well, Feynman integrals are special. They are these periods. There are only countably many of these periods. And actually now you should even think of, if you want, in here, you should insert something like this, some f, which is the space of Feynman integrals, which is a subset of periods. You can even ask, if you take now a period at random, what is the probability? Is a Feynman integral? This I don't know. Well, I would not even know. Let's remove this, because this, even that, I wouldn't know if every rational number can show up as. The other reason I mentioned this is because these periods are something, well, they were defined by mathematicians, by Donzaghi and Maxim Kontsevich. So they have a mathematical life on their own, and mathematicians are interested on their own terms. And so if you look for the mathematical foundations of Feynman integrals, what you're actually looking for is what is known about periods. So that's why I'm telling you this, is that this tells you if you want what you have to type into Google if you want to find the right mathematics.
Excuse me?
Yeah.
When you say that the Feynman rules are inherently rational, did you account for the masses at the coupling constant? Do you count them as rational too?
So the coupling constant, I don't care because those are my expansion parameter. I'm looking here at the coefficients of the perturbative expansion. Okay. Then for about the masses, that's a very good point. I didn't emphasize it. I wrote it in the notes, but I didn't emphasize it. It will be its periods if the scales, the masses, the momenta are rational algebraic. So you will get functions of the masses, for example. And these functions are such that they are periods whenever the masses are rational numbers. It's a very good point. Rational algebraic, you can exchange it. You can also go this afternoon discussion session to, if you're not familiar with what algebraic means, if you don't know what algebraic means, replace it by rational. But whenever the external data, the masses and the momenta are rational numbers, then these integrals will be periods, which still constrains them a lot. Okay?
Yes, thanks.
Good. More questions before we move on? Because now we go to
One question, what's the simplest irrational number you know that's not a period?
the simple. That's also a very good question. And as far as I understand it, because I'm usually I work with periods, there are not many numbers that are proven not to be periods, which is kind of counterintuitive because we know that most of them should not be periods, but not many of them are known not to be periods. As far as understood, the last time I checked was a few years ago, there's a handful where mathematicians have proved that they are not periods. I mean, keep in mind that if you want to prove that something is not periods, you need to prove that there's no way to write as an integral of a rational function. Okay, which is a very strong statement. The ones which I know are expected not to be periods are things like the Euler number, things like 1 divided by a period, like 1 divided by pi, these kind of things. And another thing, which is well, another, yeah, it's actually a very interesting question also for quantum field theory. It's more for the experts. We can also go to it this afternoon. So pi, we said, is a period. Log pi, you expect it not to be a period. The other thing which you expect not to be a period is this thing sometimes called the Euler-Mascheroni constant. To evaluate one of the derivative of the gamma function. So this is a bit more side comment for experts. And if you know for the experts, what is the difference between this MS scheme and MS bar scheme, it's precisely you subtract these two things. You can also see that the MS bar scheme, the modified minimum subtraction, is you remove precisely the things which would make your amplitude not be a period. So you would expand in alpha s over pi, and in alpha s you absorb things as log pi and gamma e, and those are precisely the things that are not periods. 1 over pi, log pi, gamma e, and everything else will be periods in the perturbative expansion. So there's even some weird way that physicists, when they defined them as bar, they kind of did the right thing. They subtracted all the stuff that shouldn't be there from the mathematical point of view. But the simplest numbers that I expect not to be periods should be e 1 over pi, log pi, gamma e, and numbers of this type. Those are the ones that I know. Okay. Thanks. That was a very good question. More questions? So then I guess we can move to the more like solid part of the lecture. So far, we've more looked like at what kind of things do we expect to get. So now let's actually look at what you actually do when you compute these things. The first thing we discuss is something that is actually very, well, the basis is very easy. It's integration by parts. We will not do anything else than integrating by parts, but we'll use it in a way that is maybe not so familiar to everybody. And so what is the problem that we want to solve? Well, we said at the beginning there are two problems. One is the fact that these integrals are hard to do, but the first problem was actually a different one. The first problem was this combinatorial problem that you get thousands of Feynman integrals, thousands of diagrams, 100,000 diagrams. And it's clear if you have thousands of them or 100,000, you cannot sit down and compute every single one of them by hand. You need something else. So the question that you can ask is there a basis of integrals that you need to compute? Do you really compute all the 1,000 integrals or 100,000 integrals individually, or you can find a minimal set of integrals that you compute? And that's the first question that we will answer, because before you actually try to study how to evaluate the integrals, first identify the minimal set of integrals that you should compute. Otherwise, you're just overdoing it. Okay? So that is the first thing we will look at. Okay, so how can you possibly find the minimal set of integrals that you should evaluate for your problem units? And it's here that these arbitrary exponents for the propagators come in. So remember that, well, we can also look at it again. Recap. So when I defined these things, I had here these arbitrary exponents, integer exponents. Okay? And at the time, it looked like this was just for fun. Actually, we will use that now. So what we'll do is we'll now look at these integrals that we get as functions of these integer exponents. So every integral, I look at it as a function of the exponents nu I. So I look at it as a function I, which is an integral, and it has n propagators, and I look at it as a function of these powers, these exponents of these propagators. Now,
I have a question. Can they also be massive propagators, or are they massless?
no, they can be massive. When you look at the general definition that I gave here, there were masses in there. And the masses case is just put m to 0.
Okay.
So I look at them as these, as a function of these exponents. Now, these exponents were integers, positive or negative. And so, well, I had n propagators, so capital N propagators. And so I can now represent each integral as a point with integer coordinates, with n integer coordinates. Right? So each integral defines a point in the space with just z to the power n, where n is the number of propagators. Okay? Zn is the lattice. That's a discrete set of points, some symmetry. So what I will do is I will look at these integrals as, well, every integral defining a point in the lattice. And the point defines me the exponents. And what we will do is, we have a lattice, so go and find recursion relations on this lattice. So if you manage to find linear relations that tell you how neighboring points in this lattice are connected, then you manage to find the relations among these integrals. So then maybe instead of looking at 1,000 integrals, you just need a few, because many of them are just related by recursion relations. So that's the idea, that's the goal. Find the recursion relations among Feynman integrals. And the abstract way to think about it is that you have a lattice of points. Every point sits this Feynman integral whose the coordinates of this integer coordinates of this point define exponents of propagators. So how can you find such a curvature relation? That sounds mysterious. And the idea is very simple. The idea is that you're looking at these exponents. So how can you, well, recursion relations means you want to relate things that have, say, nu equals 2 to things that have nu equals 3. So shifts by integers. But shifting exponents by integers, we know how to do it. That is the same as differentiating. So for example, if you take a propagator, here I take a massless one, but it could be a massive one, and you differentiate it with respect to one of the momenta, you get a similar propagator raised to the power nu plus 1. So by differentiating integrals, I can shift the propagators. So if you think in terms of this lattice, that these integrals sit at points of a lattice, it means that differentiation means that you jump from one lattice point to the next. So the thing that I want to do is I want now to go and say, okay, well, differentiate my integrand. I want to differentiate under the integral sign, and I do it with respect to a loop momentum, I integrate over k. And just by using the above formula, you will get, well, integrals where you have shifted the exponents of the propagator. So you produce linear combinations of integrals where you've shifted the exponents. That's fine. The problem is, what is this equal to? So because now I have this integral of a derivative, it's like an integral of a total derivative. What is the integral of a total derivative for a Feynman integral? And the answer is, it's as easy as you can imagine. Whenever you have total derivatives, they all vanish. And this is a theorem, we will prove it at least heuristically. There's an important caveat here, in dimensional regularization, they all vanish. That's very important. And we will go through the heuristic proof, and then we'll see in the proof why dimensional regularization is very important. So that means that actually what puts here the question mark can be replaced by 0. So I get that 0 equals linear combinations of integral with shifted exponents. We'll see an example in a second. So you see that you get recursion relations between different points on this lattice.
Can I ask one question at this point, which is, there's a well-known thing about anomalies arising from linearly divergent integrals where you can't shift. Now, I know in dimensional regularization you can shift.
Yeah.
But is this ever an issue?
That is precisely why it only holds in dimensional regularization. What will be important is that you don't have, well, if you use a cutoff, then you have precisely what you mentioned now. And then the proof, well, let's go to the proof and then we come back to it. If you work in pure dimensional regularization, it's not an issue because these things don't show up. If you do not work in dimensional regularization, then you would need to account for it and you would have not 0 on the left-hand side, but you would have whatever is left. And so maybe let's go to the proof and then we come back to it, because the proof is actually, at least heuristically, is that the fact that total derivatives vanish is Lorentz invariance. So for example, let's take just translational invariance for concreteness. So translational invariance tells me that if I have an integral, then I can shift the integrand. The integrand is translational invariant. It's a Lorentz invariant itself. The integration measure is Lorentz invariant. So I can shift. And the integration region is Lorentz invariant. That is very important. So if you expand it to infinitesimal p, so I can expand f of k plus p into this. And now you see that here, this is the same as what I have here. So you see that at linear order, you see that the integral of the derivative of f must vanish, which is what is written here. So it's a bit heuristic, you can go through it more carefully and you see that the integral of the total derivatives must vanish as a consequence of dimensional regularization. Dimensional regularization is important because the integration region is, well, it's the unbounded integration region. If you had somewhere an integral, say you do cutoff regularization where you had this, you integrate only up to some cutoff lambda, then this will be wrong. Why? Well, because if you shift k, you would also need to shift the integration boundaries. So what is important is that everything, including the integration region, is translation invariant. So that is why Dimmereg is important. That's why you get 0 for total derivatives. Does this
Could I just ask the question? So this is actually equivalent to the statement saying that in dimensional regularization, this, let's say, quadratic divergences for the Higgs mass do not appear.
Well, it is the same.
It's the same what you mentioned before.
Yeah, it is the same origin, just like, well, and also why, for example, cutoff would break gauge invariance, because it cannot translate. Right? Gauge transformations correspond to shifts in the momentum. So it all adds up in the end. So, but if you use dimensional regularization, then it all falls into place. I'm not saying that you can only, that this only holds for dimensional regularization. I'm just saying that the theorem, as stated, holds for dimensional regularization. Okay. So this is a very important theorem for people that calculate Feynman integrals, because it tells you that you can generate recursion relations between Feynman integrals by differentiation. There's a caveat here, it's a bit of a technical side comment, but let's go through it, especially since at the beginning someone asked about numerators, and there was this thing about can the news be negative? And I said back then already that, well, yes, I allow negative news because I can write them as, I can interpret denominators with negative exponents as numerators. And this is very important here. Why? Because if you go back and you look at what differentiation does, yes, it shifts as desired the exponent, but it also introduces a numerator. So actually, if I started with from something that has no numerator, if I differentiate, I get a numerator. Now, there are some numerators are harmless, like this guy is harmless because p squared is an external momentum, k is my integration variable, so that's a constant I don't care about. This guy is a numerator that depends on the integration variable k, which wasn't there at the beginning because I started with things that only have 1 over propagators. The idea is that, well, here it's very easy. I just complete the square, right? So I just use this as an entity, which is trivial. And I end up with a new way of writing the same thing where I have no numerator. Also here, this term has no numerator. And this term has a numerator, which is k squared, which I can interpret as 1 over k squared to the power minus 1. So this would be like a propagator raised to a negative power. Okay, so those things show up when you compute these derivatives. So you need these negative news. You see that there's no way around them. There's a caveat, which is that this is not always possible. There's some vocabulary in case people are interested in it in the literature. I'm not going through this. Yes, well, let's go through it just a little bit. These relations, these recursion relations that we've seen, is you see they come, well, you can think of it as coming from integration by parts because it's integrating a total derivative. So they're known in the literature as IBP relations. IBP stands for integration by parts. So the upshot is that IBP relations define recursion relations on the lattice. It's like a summary of what you see. And once you have these recursion relations on this lattice, you can ask the question, can you solve them? And the answer is you can solve them. And what is highly non-trivial is that you can solve them in the solution space. So it's linear recursion. So it's linear solution space. It always has a finite basis. This is highly trivial because the lattice is infinite. But you can prove that there's always, on this infinite lattice, there's a finite number of these integrals that generate all the others via these recursions. So whenever you have such an infinite family of integrals, there's enough to compute this finite number. And such a finite basis is called, in the literature, you often hear it's called a master integral. The set of master integrals is the basis choice. I should point out here that often people talk about a master integral. This is a master integral in the literature. Be careful. This is just a statement about choosing a basis for a space of solutions. There's nothing intrinsic about being a master integral. It's just a name that people use to say that they're talking about the basis element, but the way you choose the basis is up to you. Okay, so it's not that one integral is a master integral and the other one is not, and therefore one is good, the other one is bad. They're just, when you hear people in the literature talk about master integrals, they mean a choice of basis. They fix the choice of basis and they call that choice the master integrals. Yeah, that's pretty much all I want to say. One comment, which is more like a language that I may use later on. Sometimes you hear people talk about sectors. That's just saying, well, when I look at my lattice, I can, of course, split my lattice into regions where the exponents are positive, negative, or zero. So when you hear me talk about a sector in a few slides, it just means that, say, the sector where nu1 is positive and nu2 is negative. It's just the region in the lattice where some of the exponents are positive, others are negative. Okay. Are there questions? And then before we look at an example, a concrete example, that will be the last thing we do for today. Let me mention the following. So we said at the beginning that whenever you have an integral that does not depend on any scale, then the integral is zero. A corollary of this, you can think about it, is that sectors where all the exponents are, well, it should actually be the other way around, I apologize. Because where all the exponents are negative or zero, if an integral has only negative exponents, the integral is zero. I leave it to you as an exercise that you can show that. You can actually show if an integral only has negative exponents, then this integral will not depend on any scale. I leave it to you as an exercise. It's an easy exercise to do, but it will be important. The other thing is that when you have an integral where some exponents are negative, its recursion relations will not relate it to integrals where this exponent is positive. Well, at least, yeah. What I mean by that is that if an exponent is positive, it means that there's 1 over p squared to some positive power, so there's a denominator. Now you can easily convince yourself, if you differentiate a rational function, you will always produce denominators that were already there. So if you start from something where nu is negative, so it means that the term was in the numerator. If you differentiate it, this term will not all of a sudden become a denominator. So there's some kind of grading on your lattice of things that are related to each other. Okay, because things that have positive and negative exponents, so they appear in the numerator, they cannot all of a sudden appear in the denominator. We'll see that in an example. It may sound a bit abstract. We'll see that in an example. The example will be a very simple example. It will be the one loop 2-point function, massless. So that is, well, it's the integral is defined here. So it's the integral has two propagators. It has one external momentum P. The loop momentum is K. There are two propagators. One is K squared, the other one is K plus P squared. And there are these two exponents, u1 and u2, which are integers. You can easily convince yourself that u1, u2 is the same as u2 and u1. So there's a symmetry. I think that's clear from the graph. You can just exchange the two propagators. So this defines an infinite family of integrals. Right? So infinite family in the sense that for every integer pair of integers, u1, u2, there's an integral that I can evaluate. So what is the first thing I can say? Well, the first thing I can say is, well, I can now classify things into 8 regions depending on whether u1 and u2 are positive, negative, or 0. Right? Those would be my sectors. The sectors are said are just when some u's are positive, some others are negative. So what can I say? Well, we said that whenever, well, let's maybe start from, let's look at it in more detail. Let's look at the sector where u1 is positive and u2 is 0. You see that if u2 is 0 here, then this propagator here will be absent. But then that was the only propagator that depended on P. So if that propagator, if u2 is 0, there's no dependence on P. So the integral is scaleless, and we said that every scaleless integral is 0. For the expert, this would be a massless tadpole. Dimensionalization, great dimensions. The same, of course, if both exponents are 0, then, well, obviously then there's nothing in the integrand, and so the integral is 0 in dimensionalization. All scaleless integrals vanish. If u1 is negative, well, and u2 is absent, again, P is not there, so the integral is 0. But then you also have like this case where u1 is 0, so this propagator is absent, but u2 is negative, so it appears in the numerator. And then, well, what happens is you see, well, let's take nu equals -1, for example. If nu equals -1, 0 minus 1, the integral would look like this. So it depends on P. But you can easily convince yourself that it looks like this. So it is actually a sum of 3 integrals, each of which is scaleless. So
why can't I just translate it?
you could also translate it, you're right, yes. Yeah. You could also translate it, you're correct here, you could also say, just say k goes to k minus p. And then, yes, you would directly have, indeed. Thanks. It's equivalent, yes. So the upshot is that also the sector where nu1 is 0, nu2 is negative, is 0, and also where both nu's are negative is also 0. By symmetry, it means that I have other sectors that are 0 as well, right? Because I know that I can exchange u1 and u2, and the value of the integral doesn't change. Now, what about a sector where one of them is positive, the other one is negative? By the same argument, for example, if you take this guy, with the same argument that I just gave, you just expand k plus p squared, and you get sum of integrals, all of which are scalars. So they all vanish. So the upshot is that only the sector plus plus is non-zero. That's the first thing I learned. Okay. So I only need to consider those. All the other cases are trivially zero. And so what if I'm in that sector where both exponents are positive? What can I do? Well, I now write down my integrals of total derivatives here. Now note that my derivative is a vector, so I need to contract it with another vector to get a Lorentz invariant. Which vector can I pick? Well, only K or P. That's the only vectors I have in my problem. I could choose any vector, but the only ones that I care about is when V is equal to K or P. And I leave it to you as an exercise to carry out the derivative, and you see the results written down here. You have for K equals V, you get this. This is K equals V, while for K equals P, you get this. And you see you get indeed linear equations for these integrals. You can rearrange terms a little bit and you get to the following things which are a bit nicer. It's just rearranging terms. And so you see that you can connect the integrals with nu1 and nu2 with two integrals where nu1 and nu2 have been lowered by 1 unit. Okay, fine. How can I solve this? So let's look at the lattice. This will last, so it take 2 more minutes, 3 more minutes, and then we'll let you go, and then we recap tomorrow on this. So this will be my lattice, u1 and u2. These are the points in my lattice. Now, one thing we learned already, I only need to care about those when both nu1 and nu2 are positive. So everything else in this gray shaded region, I can forget about it. All these integrals are 0. That correspond to points in this gray shaded region. I also know that there's a symmetry along the diagonal because I can exchange nu1 and nu2. So I only care about, say, the lower half. So let's say I pick this integral, which corresponds to the point 7, 0. Now, if I go and I use these recursions, so nu1 is 7, nu2 is 4, you see that I can replace it by integrals where either nu1 or nu2 has been lowered by 1 unit. So 7,4, I can write it as a linear combination of 6,4 or 7,3. Okay, but now I go on, right? Each of these 2 points, I can replace it by the sum of 2 integrals where one of the 2 exponents has been lowered by 1. And I go on like this. So you lower 2 of them by 1. I go on. Now you see that here, well, by symmetry, I can just flip it over. So whatever is in the upper half, I don't care, I just flip it over. And there was also something I didn't draw, which is what would have happened if I had done here. Well, all the way down, actually. That point, I don't consider it because I know that this point here, the integral is 0. So I can forget about it. So I go on like this. I apply these recursions. Every time I cross the green diagonal, I flip it over by symmetry. Every time something has nu1 or nu2 equal to 0, I can just remove it. And I go on until I get down here to the corner. Now at this point, the recursion stops. Why does it stop? Well, when you actually look at the recursion here, they are only valid if at least one of them is not equal to 1. Why? Well, because I have this denominator here. These things were obtained by rearranging terms, and in this rearranging, I had to divide by nu1 minus 1 or nu2 minus 1, which I can only do as long as at least one of them is not equal to 1. If they're both equal to 1, then none of these two formulas applies. And so I get stuck. I get stuck here in this lower left corner, which is the point 1, 1. And that is the basis for my space. So there's a single master integral, which is the integral 1, 1. And every other integral is just a linear combination of those. And which linear combination? Well, the ones that I get from these linear combinations, from these recursion relations. Okay. So I've replaced an infinite number of Feynman integrals by just the computation of this one integral plus the solution of these recursion relations. This one integral is actually very easy to compute. Well, it's more like a side comment. I guess you've even done that probably during your QFT lectures. It's a very easy thing to compute. I just give you the expression here. It's trivial really from Feynman parameters. You can even go through it in this afternoon discussion session if you like. And so what you've actually done is you've computed this infinite family of integrals with exponents u1 and u2. And so you've really reduced the calculation of an infinite family of integrals to the computation of a single integral. Okay, I think this is a good place to stop. We'll recap tomorrow. But the thing to remember is that there are these recursion relations from Feynman integrals, which come from the vanishing of total derivatives from these IBP relations. There's always a finite basis for these recursion relations. So whatever infinite family of integrals you consider, there's always a finite basis of integrals that you actually need to compute. How large the size of that basis is, that depends. It can be hundreds. So if you start from the 100,000 integrals that at the beginning, that I mentioned at some point, there you had to compute 1,000 integrals. But it was still a factor of 100 less. Okay. So in the end, what you always compute is the basis of integrals and not the individual Feynman integrals. And what we will do in the next lectures is we will start from there and see what can we say about this basis of integrals and how can we actually evaluate them. And we'll not do it as you learned in QFT by, say, doing Feynman parameters, but we'll use a bit more sophisticated techniques. I think this is a good place to stop. So yeah, thank you very much. And then we can stop here. You can ask questions now, or otherwise we can reconvene at 2 p.m. this afternoon, 2 p.m. Central European time. And you can ask questions, or we can also just go through some of the items that I just brushed over today during the lecture.
So, I have a question. Well, just so when I look at all these discussion, these nice mathematical structures or whatever you discussed is really something which you get in dimensional regularization. So this is.
I would turn it around. I would say that people have studied it in dimensional regularization because that is the workhorse for doing computations.
Mm-hmm.
I'm not saying it cannot be done with other schemes, but people don't look at them because for all practical purposes, people use dimensional regularization.
Okay. So you might say that if you look at other types of regularizations, you might get similar results in some other form.
Maybe, and actually,
but it's
maybe now a bit technical, but actually what underlies this, well, so what's actually happening here is you classify things up to total derivatives. So actually you're constructing some cohomology groups of something. The finiteness comes from, like, you have theorems that tell you that these cohomology groups are finitely generated and things like that. All that is independent of the regularization scheme. It's more like what cohomology theory you actually use to describe your regulated theory. That is mathematically what's happening. So there are very likely there are similar relations for other schemes, which may be more complicated, maybe easier to be seen. But mathematically, it could for sure be done. It's not that this is intrinsic to dimensional organization. It's more that what underlies it here is that you're constructing cohomology groups, the RAM cohomology groups of some type for a certain type of objects, which is independent of dimensional organization. Okay, there's not seem to be any other questions. I guess we can stop here and then, yeah, we can either continue the discussion this afternoon or otherwise we continue the lecture tomorrow.